Thank you. I really have nothing left to say because Noah did it all, yeah? So I mean, you'll essentially hear you'll hear another version of the same thing. I want to talk you through a discussion of a particular trial which was studying targeted therapies, and the problem that we are focusing on here is to find the optimal eligible patient population for targeted therapies. So actually what you see here is you see on the horizontal axis there are like different diseases, different cancers. On the vertical axis, different molecular aberrations. And this is under a simulation study. There's like some simulation truth. I believe the simulation truth for the three squares that are darker here. For those for a subpopulation described by those three squares under the simulation truth, the targeted therapy actually does work better in a well-defined sense. And what you see here is a summary over massive repeat simulation to see how often do we recover that. So it actually does quite well. I'll eventually talk you through that one. Before we get there, kind of to make my point of how we proceed with the actual trial, I want to talk about another project where we did something very simple. So in a few slides, I'll briefly talk you through a very simple method of finding the subpopulations. It's more than a straw man, but like the punchline of this first discussion will be that there's something that we want to separate and that we shall do in the second discussion. This is embarrassing. My co-authors disappeared. This is joint work with Yanxun Xu at Johns Hopkins, Yuan Chi at North Shore in Chicago, and I believe Yuan Chi will actually be here next week, right? So the first one is together with Yuan Chi. The second one is then together with Don Barry and a clinical collaborator. And if you actually care, verbatim copies of the slides are online at this URL there. And I really don't have that much to say besides it all having been said already. I don't have really those many slides. So please feel free to chip in any time. I thought it actually worked very well during Noah's talk. Ask as we go along. If something were like requiring some longer discussion, I'll simply say so, yeah? So please comment and ask as we go along. I think we have enough time and it will still be done early. So I'll start out with this simpler problem. This is based on a paper with Yanxun Xu, Yuan Chi, and Lorenzo Tripper at Dana-Farber Cancer Center. What's coming up is a very simple process, a very simple design to find a subpopulation of patients who most benefit from a treatment in proceeding in a Bayesian fashion. Don't expect anything deep and difficult. It's not. It's all based on the assumption you have a relatively small sample size, so you cannot do anything way too complicated. So let's assume we have a set of potential treatments labeled 0 through cap T. 0 might be the notion of a control. We have a binary outcome, success and failure. And we have a set of baseline covariates. Let's assume those are all protein markers, or in one particular application, those are actually protein markers. And now we want to find the optimal subpopulation of patients described in terms of these protein markers that might best benefit from different treatments. To get there, we want to divide the patient population. We want to subdivide the patient population into subsets that, formally speaking, become a partition. So we introduce a partition of the covariate space into an unknown number of subsets. The notion being for each subset, another treatment might be optimal. And here's a one-slide summary of how we do it. Nothing deep and difficult going to happen. I can only draw it for 2 markers, but obviously the same thing works for more. Let's assume we have 2 markers in the first square. You see x1 and x2. and they define our patient population, our covariate space, and we proceed now in multiple steps to define a partition of the covariate space. First step, we split the patient population into two halves by split by thresholding on one of the two biomarkers. And then for each of the so-created subpopulations in the next step, we can split them again on any one of the markers. In this case, we split the second subpopulation on the second marker. And in the last step, we do the same thing yet one more time. In particular, there's no restriction. You can split on the same biomarker multiple times. As indicated in this cartoon, the split is always on the median. So we always split on the median, but the median is defined always relative to the respective parent population. So we don't choose the threshold, we only select the biomarker. That will make it feasible to work with this. In this particular case, all what we have to write down, all what we have to record to describe this partition is, we have to say that in steps 1, 2, 3, we split at biomarker 1, then biomarker 2, etc. I just need the list of markers on which I split it. That's all I have to find. This is just describing what we just went through in the picture. The splits are always on the median relative to the respective parent population. And thus all what we need in the end to record one of these partitions is just we need to record the sequence of covariates on which we split. So that outlines the process. All what I have left to do now is I have to describe you a probability model for the response, and I have to talk you through the criterion by which we actually select the covariates along which we split. And nothing difficult is going to happen. The sampling model for the response is actually as simple as it could possibly be. We have for each subpopulation, so the subpopulations are indexed with the little m. So if you have a patient whose covariates fall into subpopulation S sub little m, and you consider treatment T, then we just assume a Bernoulli with success probability theta mt. So we introduce a separate parameter for each treatment in each subpopulation. And I think we had, embarrassingly, I think we had independent beta priors on those, yeah? Without any of the fancy dancing we heard before. So this is the sampling model. Since we'll proceed in a fully model-based version, I'll also have to talk about the probability model on the partition, so that we can select one or the other partition. What we'll simply do is, since the partition is indexed by the choice of covariates on which we split, if I introduce a probability of splitting on one or the other covariate, and a probability of stopping to split at some time, that's all I need to ever tell you, yeah? And on top of that, there's a maximum number of splits. So I'll give you V sub j, which is the probability of splitting on any one of these covariates. In the absence of any other information, those could all be the same. And I give you a probability of stopping the split, and that way you can write down the probability for any partition. For example, the partition on the previous slide, I think in the first step we split on the first covariate, so that would be V1. In the second step, I think we split on the second covariate for the second subset, on the first covariate for the first subset, so that's V1, V2. And then we stop splitting on some of them and split one more time on the first covariate on one of them. It might actually be different from the picture on the previous slide, but it could look something like this. So products of these probabilities determine the probabilities for the partitions, because it's essentially putting probabilities on a generative model to create these partitions. And we complete the model with independent priors on the subset and treatment-specific success probabilities. Now we have a full probability model. We have a process. So I think we are almost done. We still have to actually implement the trial. I still have to tell you which treat. Yeah. Say again. M. M as in Mary. Oh, row n. A partition of the. Oops. You probably don't really need the n. Row simply indicates the partition. The n, strictly speaking, means you're creating a partition of n patients. although we create a partition of the n patients just by partitioning the covariate space. So you could actually drop the n index, it's superfluous. It should not be there. You could imagine that for a larger number of patients you allow a finer partition. Things like this could make sense. So I still have to decide which treatment to assign to the next patient, and for that we work with posterior predictive probabilities. So what you see on the right hand side, we have a complete probability model on the previous slide. Yeah? There was a complete probability model on all outcomes. Under that probability model, you can find the probability for the next patient recording success if the next patient were assigned to treatment T with particular covariates and in the light of the data, integrating out all the unknown guys. Yeah?
When you split on the median, do you want to make sure that all the treatments are in each subgroup? Or what happens if that split leaves out some treated patients and you do not have a full set of treatments and everything?
One could constrain to that. We actually didn't. Pointed answer to your question, if there is no data with respect to a particular treatment in a particular subset, then the posterior is equal to the prior. That might... Sorry?
Do you still retain that split?
Quick answer, yes. Longer answer, we have a maximum of 3 splits. So we have a maximum, we allow a maximum of 3 splits, and in the actual implementation, we only start adaptive allocation after an initial burn-in, after a minimum number of patients. We probably never really ran into the issue of not having a particular treatment in a particular subset, because it would seem silly not to restrict to that, but I don't think we did, yeah.
And do you allow the covariates to be categorical?
In principle, yes. In the implementation and the example, they are continuous. If they are categorical, the split, if they are ordinal, the split becomes even easier. If they are general categorical, it gets a little bit hairier, but not impossible. Cheap answer, replace the categorical by a set of binaries, and then it's easy.
Well, that's the problem there. If you do that, then you get singleton splits. You get one, say suppose you have a covariate that's race.
Yes.
Think race is important. Then you either split on white and non-whites.
Oh no, then you split like into whites and non-whites, say.
Right. Is that a good split?
Not necessarily. What we have in mind here is actual biomarkers that are recorded continuously. But in principle, the same thing could work with binary covariates. Then you don't even have to define a threshold. And then you probably don't want to split a second time on the same covariate, because that would be silly. So we didn't do it, but in principle it would work, I think. This is just the posterior predictive probability of success for the next guy under a particular treatment, averaging here in particular over the random partition, which you can do. Yeah. Then here's now the actual design. For an initial run-in of a certain number of patients, we allocate equally to all treatment arms. So that gives us some initial data set. Just the usual kind of rule of stopping an arm for futility. If an arm looks really bad in terms of posterior predictive probability, you should not continue allocating to it, which we formalize here. If the posterior predictive probability of success for a particular arm is worse under one treatment than any other treatment for some typical covariate values, then we don't continue considering it. It's actually not too important, that rule, but you can include such rules. And if all treatments except for one are excluded, then of course you don't continue anymore, because there's nothing left to decide. As long as we continue after the initial run-in, we do actually aggressive adaptive treatment allocation by allocating for the next patient the treatment that looks best in the light of the current data. Don't want to defend this as being particularly smart. It's a little arbitrary, just trying to allocate patients to what you believe to be the best treatment for them. This is just a picture of this design. You can see To the left of the bar is the initial run-in when you do equal randomization. To the right of the vertical bar, we do adaptive allocation to the random subgroups, where as we go along, we build up inference on the random subgroups as inference on a random partition of the covariate space, which is indexed by this particularly simple way of just sequences of covariates on which we split. That's it. The main reason why I wanted to show you that was just to complete the description. At the very end of the trial, we can actually report. We can report subpopulations, and for each subpopulation, we can report the optimal treatment. But the main reason why I talked you through this was because I want to point out one thing that happened here, and it also happened in many of the earlier discussions that we heard on finding the subgroup of patients who most benefit from a treatment. What we really did, so in the previous 3 slides, I talked you through a probability model. The probability model for the response included a random partition of the patient population into subsets. And that random partition, I should have pointed out, I could have simply said we do a cart. We do a baby cart of 3 levels only. That's kind of what we do, right? That random partition introduces a regression that looks a little bit like a cart with the binary outcome. Sorry? Right, so it's a card that it's a pruned one, yeah. I just called it card now because I want to emphasize it's really a probability model for the response that we built there. Because for each of the subsets, I have like the subset and treatment-specific success probability. And then we did a funny thing, and nobody screamed, yeah. So in the probability model for the response, in my sampling model, I introduced this random partition because I wanted this card kind of thing, yeah? And then I simply used exactly the same subsets that I used for my sampling model. I used the same subsets for my random treatment allocation and for recommending different subsets. There's something natural about doing that, but it's not at all necessary. Actually, you might want to argue that for prediction, like just for my sampling model, I want to have a model that fits well. You want to have a reasonably complicated model. You might want to have some black box. If you have a large number of patients, you might even do something like the BART or so. So for my posterior predictive inference, I want to have a model that fits well, that might include very fine splits, etc. That's one thing. I would argue a totally different thing is when you report different subsets with optimal treatments. There you probably want to only report subsets that have clinically interesting different estimated treatment effects. Like you could have a statistically highly significant difference across 2 subsets, but the difference might be so small it's not of any clinical interest, right? Or you might have a small subset with a statistically very significantly different effect, but it might be such a small subset that it is silly to entertain a notion of like a different treatment for that small subpopulation. Or same thing, in other words, when it comes to the decision of reporting these subsets and maybe reporting the winning subset for each treatment, it's really not natural to use the same. At first glance, it might seem natural to abuse the same subsets that we built with our card tree, but it's really a different kind of a problem. Because in that case, we probably want something that's reasonably coarse and big, because then it becomes practicable and clinically meaningful. And we might deliberately want to ignore some differences that we know that are there because they are not of practical relevance. So what's coming up, and you did, yeah?
I have just one question. It seems a little bit dangerous because after the burn-in period, you don't really have randomization. It's deterministic, right? I mean, maybe you could change that rule.
I plead guilty. But as you say, it's very easy to change. Now, that's when I remember when I think you're referring to the last line on the previous slide where the allocation of the next patient was to the optimal treatment. I mean, that's easy to fudge. Like if you can randomize over all treatments within plus minus epsilon. Sorry?
Is there any reason for goodness of fit? How to create it? There may be some cases may not be important, some cases may be really nice.
You mean how good is the fit of such a model? Probably horrible, but we are talking about reasonably small sample sizes, so you don't really have the pretense of getting a really good fit to some unknown true response surface.
Some partition may not be important. Some partition may just come. So if you want to work, number of partitions will be very large. Right? So maybe some benign increase.
You mean you might want to you might want to control the number of partitions? We do by allowing it most free. And you can also tune it by, there's this prior parameter, it was the V null, which was the probability of stopping the recursive split. Make the V null big, then you will encourage even more parsimonious trees. So I'm not too worried about the sampling model. It's meant to create a decent fit. It's far from perfect. Yeah? The main issue is that we don't split at optimal thresholds, we just split at the medians. But even such a coarse model is probably finer than what you really want for the decisions.
No, maybe we are splitting too much. So maybe we could do some pruning.
One could. One could. But you're leading me down a slippery slope. You want me to prune such that I get beautifully looking subsets that I can report. I don't want to report those subsets. I just use those subsets to get a good prediction. The report I consider as a separate decision problem. Actually, I should have said the fact that we're using the card model, which also happens to produce subsets in a covariate space, that actually wasn't important. It could have been any other model that might not create subsets. I could have used wavelet decomposition of the response surface. Did I convince you should separate these two things? They're really like two different aspects. So one thing is the probability model that I use for my posterior predictive inference. At this moment it's just the sampling model, and when you integrate with respect to the partition and the parameters, then it becomes the predictive, right? And a totally different thing is the action, and Noah already talked us through that notion, yeah? I would want to separate it even cleaner. Like a totally different thing is the action of reporting these subsets, where I can report, where you can report, in this notation, A of X would be the subset that a patient with covariance X falls into. That's a totally different action. And there's no need that the two of them should be based on the same representational model. They're really different. And we'll fix that in the next application. So now you can pretty much impute what's coming up, yeah? Should I still go through it? I'll try, yeah, just so you. So this was just a table of simulation results. So here's another approach, another trial. And I'll talk you through a way of kind of answering the same question as before with a slightly different model, yeah? The sampling model will actually be a bit more complicated because it's a more complicated problem, but that's incidental, that's not important. The important thing is that I'll totally separate the two things. So this is a trial that's actually currently still running at MD Anderson, but not much longer here. The trial is trying to essentially answer the question, does targeted therapy work, yes or no? They recruit patients across different diseases. The outcome is progression-free survival. For each patient, we record whether the patient gets targeted therapy or control. Of course, each of these is really a whole bag of treatments, right? But we just want to compare in the end targeted therapy versus control. Outcome is progression-free survival, and there's a number of mutations that are being recorded. This is actually not the data from the randomized trial. This is observational data from earlier. And in that observational data, many of the aberrations are not recorded for many of the patients. Like, depending on what's the disease, some of these aberrations might make sense to record or not. So these are not missing. They were simply never ordered. They were never asked for. So the primary aim is to determine whether targeted therapy works, yes or no. But what we want to focus on in the remaining few slides is a secondary question, namely we want to do adaptive treatment allocation, and in particular we want to find a subset of patients who might best benefit from targeted therapy. The answer to the second question is like the picture that we saw on the title slide. According to disease and mutations, you indicate for which you make dark blue for those combinations where targeted therapy works, and white for those where it doesn't work. This is just telling you that the trial enrolls patients who are eligible for some FDA-approved targeted therapy. And we focus now on that secondary aim of finding the optimal subpopulation. And in doing this, I shall now try to fix what I pointed out we did sloppily in the earlier study. I will try to cleanly separate these two aspects. There will be one model for progression-free survival, and there will be a totally separate discussion of finding the winning subset. This is just showing you the data from an observational study. You can't really tell anything because it wasn't randomized. Yeah. There's one more minor twist to that always tickled me a little bit. What we'll need for the sampling model, we'll need essentially a survival regression, right? Because we need progression-free survival as a function of the covariates. Now, on many of these patients, some of the covariates are not recorded. So what we need now is we need a survival regression with a variable set of covariates. And some of these covariates are deliberately not recorded, so it would be kind of silly to treat them as missing data. So, and it shouldn't be difficult because clinicians can certainly do that. Yeah? If you give them a set of covariates that are recorded, they'll use that set to make a judgment of what the outcome might be. Yet for statisticians, it's such a simple problem, regression with a variable dimension covariate set. Yet I think there's no canonical answer to it. It's something that always tickled me. End of the footnote. Yeah?
How do you handle disease in your model? In your previous slide, you had different types of cancers. Right?
Good point. I should have pointed it out. Disease becomes part of the covariate vector. That's categorical, yeah. Sorry, it's a set of binaries. No, we are not going to do the splitting thing. It's going to be a different trick.
So your tree, when you split, you don't split on disease.
We are not going. There's not going to be splitting games now, yeah.
Oh, so this is
completely different. Actually, even to the point that the mutations are just binary. Either they are recorded, either they are there or not. Yeah, the patient has the mutation or not. Good question. I won't tell you for a while, deliberately.
If it is, then the two models can't live in the same space. You can't have a prognostic covariate. You can't marginalize over the covariate using the proportional.
Yes. One-line answer, it will be a nonparametric Bayes model based on random partitions, blah, blah, blah. But actually the more relevant answer, to discuss the optimal solution, to discuss the optimal action, I actually don't have to tell you what the probability model is. I don't have to tell you what the sampling model is. You can discuss the solution of the decision problem, just assuming there is a sampling model, but it actually happens to be that one, yeah? That business with the varying fraction of observed mutations, it tickled me. It's probably not so relevant in the actual trial because in the observational data from earlier, many of the mutations were missing systematically. In the data from the randomized trial, I think we actually have almost all on all patients. Yeah.
For those missing mutations, when they're not missing, are they coded 0, 1?
Yes.
Then you can code the missing as 0, 1, 2.
As 0 or as 1 or as both?
You have 0 and 1, and the missing coded as 2.
Oh, as 2, not as 0, 1 as well. Eh.
If you're worried about the order of 0, 1, 2, you treat them as binaries.
Yeah, no, I mean, it's good. It would be good enough for government work, but you shouldn't have to do that because, I mean, as a clinician, if you know some covariates of your patients, that's what you use. I mean, you might not know your patient's preferences in music, and maybe that's totally irrelevant. Yeah.
So you're talking about surrogate splits then. I mean, when you say a physician knows something about mutation, and that mutation is not recorded, the physician is using something else in its place. So now you're talking about surrogate variables.
The physician might simply not make use of that. Like if there is an unknown that you don't know, then just don't.
Something else in its place then. I mean, if it's not
Or you just use the information that you have.
yeah, so implicitly there's some sort of a surrogate covariate going on.
No, not necessarily. I mean, it's just something you don't happen to know. Like Noah and me, we cluster together in terms of some of our preferences and statistics. So on the basis of what you know about us, you might think we cluster together. There might be things you don't know about us in which we are totally different. Yeah, you might be listening to really weird music. Yeah. So it's just for that decision, for that judgment.
It has to be done. I mean, unless
Why? You simply don't know what music he likes.
sample because you don't have that thing, right? I mean, the fact that you're retaining the sample, you're missing some covariates, and something else is.
No, I think we are too much brainwashed to insist on seeing the covariates. They're simply not there. But I really didn't want to get stuck in that. There was a footnote that tickled me because it seems like a really simple question that my little brother could answer if I had one. Yeah. But
So are you saying that you're systematically not saying you both like dresses?
say again.
Are you systematically saying you both don't like dresses, or something important that we might need?
Yeah, but if you don't know it, you can't use it for your inference, right?
You're suggesting there's some information there that you're disguising systematically.
You think that you could actually impute these unknown things.
Well, there's something about your character, you two, that we could use that information.
Yeah, then why don't you just simply use like what you know about our character, period, yeah? But let's not get off track on that one. For the moment, I'll not tell you about the sampling model. It was actually good that you asked, yeah, because that allows me to emphasize, I'm not going to tell you, yeah? And the beautiful thing is you don't need to know. And I think that's important because the moment that you know, you might get tempted to use whatever features of the sampling model to do your decision. And I think that's fundamentally wrong, even if it's reasonable, yeah? So let's talk about the decision, just assuming that there is a sampling model, but I don't need to tell you which one. So we need notation for the decision. To describe a subpopulation, I have to tell you the set of covariates, in our case, the set of mutations, and you might always want to include the disease. And for each mutation, I have to tell you whether I want the mutation or I don't want to see the mutation. Then we could describe the desired decision as simply a pair of the set of covariates that I want to look at and what levels you want for them. In our particular case, the set of mutations, whether they are there or not, and which disease. So we want to decide on that bold phase A. That almost characterizes. So I think it's important in a decision problem. It's important to actually state the actions. Yeah, you had it beautifully as your script D, right? It's just good practice. Yeah, state the actions that you're after. So these are the decisions that we're after. Those decisions are totally unrelated for the moment from how we parameterize our probability model. I don't have to tell you about that probability model yet. That also means we don't even get into any of these tricky issues like multiplicity controls. We don't have to talk about statistical significance versus clinical significance because I'm not even going to talk about the sampling model yet. In particular, that allows me to talk about variable number of covariates for the moment because I don't even tell you yet what the sampling model is. I liked your utility function. It was a good one. All what we need now is, so I told you what we're after. We're after that particular action, like we want to choose that type of action. I have to give you a criterion, and then we're essentially done, yeah? And your criterion was essentially some kind of sensitivity and specificity, right? Here's another criterion. We could say we want to have, I think in plain English we can agree on that one, yeah? Our outcome is an event time, progression-free survival. We want to find a subpopulation with something like a high log hazards ratio. And I still have to define what the log hazards ratio is, because short of a proportional hazards model, there is no such thing as a unique hazards ratio, yeah? I simply have to tell you how exactly we average the thing. We probably want a large size population, because otherwise it's clinically not of interest. Like, you don't want to have to develop a treatment for a single patient population. And for all kinds of reasons of communication and plausibility, I would prefer to describe a subpopulation on the basis of one or few mutations rather than on the basis of too many. Yeah? And how exactly you formalize now the red, the brown, and the orange, that is a little bit arbitrary, like any time you choose a sampling model or a prior or anything. Here's what we did. Remember the title slide? The winning population actually were these 3 dark blue squares. So there is a sum over the blue squares, where each blue square is determined in terms of a combination of the covariates. And what we want to have for each of the blue squares, I want to have a large log hazards ratio between targeted therapy and standard care. I want to have a large population size, that's that NA, the brown NA in the numerator. And I want to use few covariates. Remember, cap I was the set of covariates, the set of mutations that are used to describe the subpopulation. So by dividing by the cardinality of that, I favor a small set of covariates. Now, if you want to critique the particular way of how I formalize the red, the brown, and the orange, that would be a very fair game, yeah? Because it's not at all obvious how exactly you do that. It's a bit arbitrary. And I owe you an explanation from where the size of the subpopulation comes from. We simply estimated by the size of the subpopulation in the observational data from earlier. That's essentially it. If this is our criterion, if U is our criterion, if I say that my relative preferences for different choices of subpopulations are described by the red, the brown, and the orange, then what you simply have to do is you have to choose the action, you have to report the subpopulation that maximizes the criterion. That's the winner, right? In doing so, there's a minor problem. The criterion includes unknown parameters. Those are parameters that feature in the sampling model. So what we have to do is you can argue you have to average with respect to those, and then you get like the criterion and expectation. If we call the criterion utility, then this becomes the expected utility, and I think that was exactly what we saw before.
So alpha and gamma tuning parameters?
Yes. And don't ask me the next question, please, because I have no answer. I have no clue how to fix them, yeah? So the model answer would be, I'm not sure how to fix them. The honest answer would be, what's going to come up eventually is what we are building here, like we're building up to a design, right? Eventually for this design that was created on the basis of all these considerations, at the end of the day, that thing has frequentist properties, right? So you can evaluate these frequentist properties like under massive repeat simulation. And then what I'm going to do is I'm going to turn the knobs on the alpha, beta, and gamma until I see what I want to see. Like kind of reverse engineering, yeah? But I'm sure many of you have seen that before.
How do you generate the simulated data to do the tuning?
That is easy, because there's something nice about frequentist statistics. It's easy. No, sorry, I couldn't resist that comment. Yeah. So under this, for example, if I am after a type 1 error, then I simulate under the assumed null hypothesis.
No, you need a probabilistic model to simulate the null hypothesis, right?
So under the null hypothesis, there is my overall null is that the thing is not effective for nobody. That's an easy one. There are trickier ones, like we are going to talk later about, we might talk later about things like false subgroup rate, like if the truth is that there is a winning subgroup, and I report another subgroup, that's also an error, right?
So you are not simulating the data, you are just commuting the treatment labels.
No, we are going in the, like eventually in the last slide, we are going to simulate data.
You have to simulate the joint distribution of the covariates.
Oh, that's easy. I'm going to use the empirical distribution from my data. Because that's only the distribution on the covariates. That's kind of a nuisance that I need, yeah? But that's like any time you're talking about regression, when you talk about frequentist summaries, you need to make some assumption about the distribution of the covariates, but you probably don't want to.
With nothing, right?
Sorry?
You're starting with nothing.
Could be the case. Truth is, in this case, we actually have historical data from an observational study. Another thing is that at the end of the trial, we actually have something. Like we only have to make inference about the winning subpopulation at the end of the study.
But would that be too late to tune this? Because assume you have to tune this at every step.
It's not too late. It might be dishonest, or.
That's the most honest statement I've heard.
No. So, I mean, in this particular case, we have observational data. Like, you make some reasonable assumptions about the distribution of the covariates. Same thing in different words. I think it would be overkill to model the distribution of covariates, yeah? I mean, you could, but it would probably be overkill. So that's it. And one of the beautiful things to see here is what you did not see. I didn't lose a word about the sampling model, yeah? Like, I can tell you what's the answer without telling you what's the probability model. Like, we need a probability model, otherwise this integration doesn't make sense, but I don't have to tell you which one it is. I think this came up today already once, the notion of enhanced treatment effect in Foster and others. That's kind of related to that, yeah? Like they're trying to find the subpopulation A with the maximum enhanced treatment effect. Just that we enhance the notion of enhanced treatment effect by not only going after a subset with enhanced treatment effect in terms of log odds ratio, but we also take into consideration clinical plausibility in the denominator and practical use in the numerator. And that offset here, minus beta, that gives us some clinically minimum meaningful difference. Clinically minimum meaningful log hazards ratio. So this is the misspelled decision problem, and the beautiful thing is that it doesn't really matter what the probability model is. Now we have a probability model. Maybe I'll just summarize it in words. And if you're interested, I'm more than happy to tell you the details. But the details are kind of ancillary to the bigger enterprise of that design here. So in plain English, here's what we do. For the probability model, let's talk about predicting the outcome for the next patient. To predict the outcome for the next patient, I take the covariance for the next patient, which is now the mutations that are recorded and the disease. On the basis of the covariates for the next patient, I try to cluster that next patient with some of the earlier patients that look similar to that patient. And then my prediction for the next patient's outcome is simply the average of the outcomes from the earlier patients that he or she clusters together. Then I'll average over that clustering business. So the clustering happens with certain probability. The next patient joins a cluster of some earlier patients. I average over all these cluster assignments with appropriate probabilities and average the prediction accordingly. And then we even average over the partition of the earlier patients, and that's what we see in the end.
You average the outcomes when the census progression is about the time.
That's not a problem. So once you do simulation to average over the random partitions, the censored event times are not a problem because I can actually easily impute them and average accordingly. Yeah. In the course of when you do Markov-Chain Monte Carlo simulation, you have for each cluster so in the simplest case for each cluster I might have a log normal distribution for the progression-free survival time. conditional on the parameters of that log normal, it's very easy to impute the missing time, the sensor times, right? And you can complete your MCMC now, right? This is not critical how exactly you deal with the censored observations in some coherent way, yeah? If it's just a log normal, you might just as well just take the appropriate normal CDF, yeah? So that's exactly what we do. Oh, here you see now an explicit statement of the full covariate vector is the disease type, the mutations, and there might be additional baseline covariates like age, etc. Oh, there's one big advantage of that clustering business that I just talked you through. You can talk about assigning the next patient to one of the earlier clusters on the basis of whatever covariates you happen to know for the next patient. If you don't know some covariates, you simply don't use them to make the judgment. So that's one of the reasons why we picked that particular model. So this is what I just talked you through. We introduce random clusters, random subsets of, we arrange our patients in a random family of subsets. And then for each patient, we find the group, we find the cluster of other patients that are most similar to that patient in terms of the covariates. And then conditional on an unknown cluster membership, our prediction might just be the mean progression-free survival specific to that cluster, and then we average over these cluster memberships, and that gives us our posterior predictive inference. For a complete description of the probability model, I would have to talk you now still through the notion of the random partition. Like partitions are kind of awkward random quantities because they live on an awkward space. But there's one beautiful thing about partitions. There's only finitely many, right? I mean, awfully many, but finitely many. So in principle, you can write down anything non-negative, and you can always normalize it. And that's exactly what we do. So we have a probability model for a random partition indexed by covariates, and that's what we use for to formalize that business. Blah, blah, blah. No, really blah. I mean, blah, 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 because you could have used any other model. Like, if you could have replaced what I just jumped over, you could have replaced it by a BART, by a CART, whatever is your favorite model, yeah? This is just, again, a short summary of the probability model. The probability model involves random partitions. I probably shouldn't have said that loudly because we are now in danger of falling into the same trap as before. My sampling model actually also involves random partitions, but the subsets of that random partition have nothing to do with the decision that I have to report, yeah? Because you probably want much finer subsets there, and they are random, and we are averaging over them. We never want to report them. In particular, though, that model allows me random size covariate vector regression, which I thought was a nice feature. And I would still like to talk about the simulation. Oops, at this moment I'm done, yeah? Because I almost done, sorry. At this moment, I talked you through a criterion to report the winning subset in the end. I told you that we'll actually average that criterion with respect to the posterior predictive distribution under some probability model. I briefly talked you through the probability model, telling you it could have been any other. We are done. In principle, I mean, implementing the thing is, of course, implementing the thing is a bear, but in principle, that's it. So there's one more issue. There were these tuning parameters, and there's the issue that nobody would trust our answer. Yeah, I mean, in a way it's coherent because it's based on a complete description of all uncertainties and all preferences, etc. But there's lots of little gears and bits and pieces to it. So to really calibrate things, you want to look at some summaries. In particular, we want to look now at frequentist summaries like type 1 error, etc. Looking at such things like looking at type 1 error or looking at the probability of selecting the correct subgroup, I have one very simple problem. In my sampling model, in my probability model, there is no notion of a true subgroup. Yeah? There's no notion of true subgroups in the probability model because I separated the decision from the probability model. So in order to have meaningful definitions of error rates, I have to introduce the notion of true subgroups. What we simply do is we take the same criterion as before, but now instead of averaging with respect to the posterior distribution on the parameters, you can average now with respect to whatever is the assumed true probability model on the parameters. Then you get something like, let's call it true expected utilities, and then I call the true subgroup the one that wins under the true expected utilities. So those are the expectations of my criterion under the simulation truth for generating the data. And that way you can create something like true subgroups. This is now back to the title slide. In one of the simulation scenarios, the simulation truth was on the left side. So the simulation truth is a sampling model for the data. To translate this into a true set of subgroups, into the blue squares, I did exactly the trick from the previous slide, right? I averaged my criterion with respect to the sampling truth of the probability model, and the winning guys are what you see here. So these ones are the optimal subgroups, means this describes the patients who truly benefit, who most benefit from targeted therapy under the simulation truth. What we did then was we ran our little design 1,000 times, like 1,000 repetitions. We simulated hypothetical outcomes of the trial, and then the blue shades tell you how often do we actually report these subpopulations. It's not too bad. See, if it were to perfectly recover the truth, it would be too good to be true. I didn't tell you the sample. Yeah? Yes. So under this. Sorry?
Is it 15 you have there, or how many?
More than 50. The winning subgroup here are colon lung cancer patients with this mutation, lung cancer with that, lung cancer with PIK3, breast cancer with this one, etc. It's not only 15 because you have combinations of the squares. There's a combinatorial explosion. So there's awfully many. There's 15 blocks. Yeah. But you can put them together like Legos. Sorry?
7 squares, right?
Under the simulation truth, I didn't count it yet, but under the simulation truth, the winning subgroup is the union of these 7 squares. Like going back to the earlier notation, the best bold phase A under the simulation truth are these 7 squares. And this shows you averaging over many repeat simulations how often we hit these 7 squares, and it's not too bad. Yeah? If we were to exactly hit them, it would be too good to be true. And I don't remember the sample size of the simulation, but it must have been something reasonable. Yeah? Probably around 200 patients, something like that. And now just summarizing how good these results are, we report summaries under that repeat simulation. So in particular, there's one more thing. Since it's not just hypothesis testing, there's not just 2 alternatives, right? There are many alternatives. There could be the overall null. So the overall null is the thing doesn't work for nobody not. The overall alternative is targeted therapy works for everyone equally well. So we call this H0 and H1. And then in between, there are many things in between, because targeted therapy could work for any subset of patients. So there's more than just 2 error rates we have to report. So the very first one in the left, the very first one here, this is simply type 1 error. Then this one is simply call it like vanilla power. Yeah, this is the probability of reporting H1, that it works equally well for everyone, given that H1 is truly it is truly working for everyone equally. And then there are many variations, like it's possible that it truly works for a particular subgroup, like a combination of squares. And then this is the probability under repeat simulation. So these are now not posterior probabilities, these are frequencies under repeat simulation. Then this is the probability under repeat simulation of correctly reporting the true subgroup. So this one is desirable. This one is false negative rate, assuming that the null is not true. What's the probability of reporting the null? This one is the probability of reporting a subgroup that is not truly the best one, and this one is the probability of reporting the overall alternative when it's actually only optimal for a subset. This is the table down there actually is the much shorter explanation. Yeah? There's possible truths, possible decisions, and possible ways of screwing up or doing it right. This is now the honest answer to your earlier comment. We can choose we tune the alpha, beta, gamma to achieve desired rates on these summaries. That's a very typical thing to do for Bayesian clinical trial design. Because once you have constructed a design, you can pretend that this is a design that just came like out of the blue. You had an epiphany, and now you're not just treat it as a classical design, and you want to evaluate its properties. And these are actually the summaries. They don't look too bad. They almost look too good to be true. To really judge it, you would need to know what exactly the scenarios were. So scenario 1, that was we assumed that the truth is the null hypothesis. So in this case, only type 1 error makes sense to report. In scenario 2, I think the truth was H1, and scenarios 3 through 6 were like other variations. And I don't want to bore you with all those details now. So once you have that complicated model, you can also use it for adaptive treatment allocation, which we actually do, but nothing happens if I skipped it. Which gets me to the final summary. We used random partitions to do, I think of this essentially as subgroup analysis. It's like subgroup analysis with the purpose of recommending the winning subset in the end. That's all I wanted to tell you. Thank you.
A really stupid question. What is the practical problem you're trying to solve here?
Finding an eligible population for the next trial.
Right, so it's not a question of simply deciding what is it, because there's a particular point at which you start doing different things. So an early point at which you just randomize people, if I understand correctly. And then there's a particular point at which you start behaving differently.
In terms of the adaptive allocation, yes.
So the point is, at that point where you start behaving differently, it's not that you're trying to indicate what you think is the best treatment for the next patient, or is that the objective?
It's not the objective, but we actually could answer that question, and we actually used the answer to that question for the adaptive treatment allocation that was on the previous slide.
Yeah, it's because I'm just trying to fit this in the framework of what Don Berry does with these bandits, where there's a trade-off between what you would do as best for the next patient and what you would do for the future patient horizon. So what I'm not quite sure about is where it sits in that particular framework. Or maybe it doesn't at all, I don't know.
No, good question. So honest answer, the adaptive treatment allocation is really just that's a side issue. The adaptive treatment allocation is not of the type of just selecting one or the other arm of a multi-arm bandit. It's just changing the probabilities of treatment assignment slightly, actually not even much. So if you were to pin me down, are we trying to find the best treatment for the next patient, or are we trying to just find the optimal subset in the end? I would say the latter. Yes.
And you do use the reversal jump.
Yes, it becomes a trans-dimensional MCMC. We don't use the reversible jump. Essentially, you run into things like the polar urn thing. like it's a modified polyiron. And if you have ever burned your fingers on these things, we use Neal's algorithm number 8. We do a stupid thing.
Is this written up somewhere then?
It's written up and as of today rejected. If you sit here, shame on you, but all is fair. It's an archive, so if you just and I might even have the reference right here. It's that last one. And you can actually find the slides on my homepage. The reference was smartly enough only on the first title page. So in a moment I'll flip back to the title page, then you can see the URL. I would love to hear any comments on more details.
So I have another question. You talk about, you have this probability model, and which is you are not going to use in the end. You will use something different.
No. We only use one probability model. For making the decision, I don't use any features of the probability model. The decision is separated from the probability model, but I have only one probability model. Tau shall have only one probability model.
Is this something like, when you design a clinical trial, sometimes we have this design prior, we have an analysis prior?
No, none of that kind, none of that type.
Okay.
So another question, is there any information transferred from one block to another? For example, some approaches to modeling would favor a simpler model, and that would require that higher order terms are shrunk closer to zero, and that essentially means the main effect information carries across from one group to another. But if you start treating every block as being somehow in itself for estimation, that doesn't happen.
Quick answer, yes. Longer answer, we actually, in the decision, we explicitly favor bigger blocks. For example, if you could say it works for everyone with a particular mutation across all cancers, we prefer it because in the criterion there was the cardinality of the number of covariates. And even longer answer, in the sampling model, we borrow strength across the different squares in the following way. That sampling model also included a partition of patients, and we're averaging over that partition. And as part of that averaging, we also include partitions that have bigger blocks that include it's actually averaging over partitions of patients. But so the partition of patients might include patients across many different squares. And so at that time we average, because with some probability the partition might even be just simply a single subset. Then we just get one overall mean progression-free survival. The probability is probably small, but it's not.
And implicit also when you showed the diagram when you had the 7 blocks that formed the subgroup, was that all the patients in the other blocks would get the other treatment, or what is the...
In this case, for all the patients in the other blocks, standard care is ideal.
So what's the optimality in this procedure?
What's the optimality?
Yeah, is there so
It's coherent and principled.
coherent and principled?
You can't lose a bet with
you look. The pointed answer to your question is the optimality in this procedure is it maximizes what I cleanly stated to be my criterion, and that criterion, to the extent to which it's a stylized description of everyone's preferences, is our all optimal procedure. That's embarrassing because it wasn't particularly smart, and we saw a smarter one today.
So how would you actually, I missed the earlier part because I was trying to make
You missed nothing.
So how's the eye? What is the eye doing?
You're amazing. You succeeded. Sorry. Sorry.
So what was the eye?
In the end, our decision is to report those blue squares, right? The blue squares are described in terms of a certain subset of covariates, means mutations and disease type. If you only use one mutation in disease type, I preferred it to a situation where you tell me that I need to have a combination of 5 mutations in a particular disease. I find it implausible. The cap I is the set of mutations that I need to describe my blue squares. The fewer mutations, the happier. That's why the cardinality of cap I is in the denominator. If you use 2 mutations and disease type, this is a 3. If you use 5 mutations and disease types, this is a 6, plus 1. Don't ask me why we have the plus 1. We don't really need it.
You need to specify your alpha and gamma too?
Yes. The alpha and gamma should reflect your genuine preferences as a rational decision maker. Don't laugh. That was the fake answer, yeah? The honest answer is you choose the alpha and the gamma by reverse engineering. On the basis of this criterion, I get decisions and I get certain performance in terms of frequentist probabilities. To get desirable frequentist probabilities, did you notice that my type 1 error was a suspicious 5%? Like the type 1 error was a suspicious 5%, although I never designed it for any, there was no notion of setting a particular alpha level, right? This was reverse engineering. With the first triple alpha, beta, gamma, it looked awful.
So those are user selected.
That is so much nicer to say than, yes.
And the answer can be sensitive to those parameters.
And it's good, so the answer better depend on your preferences, right?
Right. But the truth is, as with everything, is there a meaningful interpretation to that? Like quantified? Is it half or quarter like this?
No, I mean, so seriously, I mean, there is a meaningful interpretation because like the alpha, beta, and gamma tell you how aggressive your preferences are with respect to these different criteria. I don't want to defend my criterion too much because I think it's really just a stylized representation that kind of goes in the right direction, yeah? Like many things in life. Fair comments, I mean, I agree, yeah?
All right.
Thank you.